Hello everyone, welcome back. In this video, I want to start discussing how to solve systems of linear equations. This is a pretty big topic that we'll revisit again in later classes, but in our class, we're just going to focus on what we say are 2x2 linear systems. That is, our systems of equations or collections of equations. We're just going to have two of them, and they're only going to involve two variables, x and y. So what does it mean to solve a system of equations or a system of linear equations? Well, to be a solution to a line, you need to be an ordered pair x comma y, that when we plug those x and y values into the equation of our line, it gives us a true statement, or in other words, it satisfies the equation of a line. Well, to be a solution to a system of linear equations or a system of equations, we're still going to be an ordered pair x comma y, but we have to satisfy or solve not just the first equation, but also that same pair of x and y values has to satisfy or solve the second equation. So we're looking for pairs of x and y values that solve all the equations. Those are going to be the solutions to our systems. So we know the solutions to our linear systems are going to be these ordered pairs x comma y that satisfy both equations. But if they're satisfying both equations of our lines, that means they are a point that is on both of our lines. But can we think about what that would look like visually or geometrically in a picture? Well, maybe our first line in green looks something like this. It has a negative slope, right? And then our second line, do it in orange, maybe it has a different slope, positive 2, just going with the example we have here. And so that might look something like this. And well, any point on this line in orange will satisfy our second equation. Any point on our line in green will satisfy that first equation. But we're looking for a point that satisfies both equations or is on both lines. And well, we can see in our picture that that is going to be our point of intersection. So another interpretation of what these solutions to our systems of linear equations are is they are points of intersections between the lines involved in our system. And so we can see in this first little picture that I drew here, well, it's possible for our lines to intersect once. And if they intersect once, then we have one solution. But there are a couple different ways our lines can be oriented in three-dimensional space. Maybe our first line looks something like this, and our second line is parallel to our first line. So it has the same slope, but a different y-intercept. We can see that if our lines are parallel, I didn't draw them perfectly parallel here, but imagine I did. If our lines actually are parallel, then they're never going to meet and they're never going to cross or intersect. And so that means we will have no solutions because we'll never be able to find a point that is on both of our lines or satisfying the equation of both lines. So we will occasionally run into the situation where we are working with parallel lines in our system of equations. And in that case where we have parallel lines, we will have no solutions. And well, there is one more situation that we will sometimes run into and we have to be aware of. It doesn't really matter how we think of our first line. Maybe it looks something like this. And so parallel lines have the same slope, but different y-intercepts. But what happens if our lines have the same slope and the same y-intercept? Well, then they're actually the same line. So if our lines are the same, then all the points on the first line are also all the points on our second line, and we have more than just one point of intersection or one solution. All the points will work, and we will have infinitely many of them. So we will have infinitely many solutions when the lines in our system are landing on top of each other, or when they're the same line, or when our lines coincide. And so when we have the same lines, that's when we are going to have infinitely many solutions. So there's three situations we have to be aware of. The first one is what we're hoping for, and it's the most common. Our lines cross at a single point, and we have one solution, and we're trying to find it. The other two situations are less common, but we just have to be aware of them. If our lines are parallel, meaning they have the same slope but different y-intercepts, then we'll never intersect and we have no solutions. Or if our lines have the same slope and the same y-intercept, then they're really the exact same line. They have infinitely many points of intersections, and therefore infinitely many solutions. So let's go ahead and see what happens in our system here. So our first line is y equals negative x plus 2. And so in order to graph this line, y equals negative x plus 2, let's go ahead and do it in green. We can start by recognizing our line is in that nice slope-intercept form, y equals mx plus b. That's the case for both of our lines in our system here. So we know the number in front of x is our slope. In our first line, that's negative 1. And we also see that constant term at the end is our b, or our y-intercept value. So our first line is going to have a y-intercept of positive 2. And a slope of negative 1. So let's go ahead and use that information to graph our first line. We'll go ahead and keep it color-coded and do it in green. So our starting point can be our y-intercept of positive 2. And then our slope of negative 1 tells us how we can get to more points on our line. Remember, our slope of negative 1 is like our change in y over our change in x, and we can always think of that as negative 1 divided by positive 1. So if this is our starting point at 0, 2. If we increase x by positive 1, then we have to decrease y by 1. So that gives us a second point, 1, negative 1. And we can keep doing that to generate as many points as we want on this line. If we do it one more time, right 1, down 1, we get a third point on our line, and that third point happens to be our x-intercept. And so now we can go ahead and do our best to draw this straight line through our 3 points. And it should look something like this. Our green line is y equals negative x plus 2. All right, so let's go ahead and get ready to graph our second line. We'll do it in orange, y equals 2x plus 5. And so if we're graphing the second line in orange, using the same kind of approach that we used to graph our first line, we recognize it's in that slope-intercept form, y equals mx plus b. We can see the y-intercept of our second line is positive 5. And also our slope m is equal to positive 2, or we can think of that as 2 over 1. And so now to generate a second point on our second line, we can use the slope. Our starting point is 0, 5. We go right 1 and up 2. So right 1 and up 2 puts us at the point 1, 7. And so then we could go right 1 and up 2 to generate more points, but now we're running out of space to graph that third point. And so here's an opportunity to talk about another way we can use the slope formula to generate points. Instead of always generating points to the right, we can also use the slope formula to generate points to the left. Because if we're going right 1 and up 2, that's the same as going left 1 and down 2. And we can actually kind of see that in our slope formula as well. Instead of thinking of positive 2 as positive 2 divided by positive 1, we can think of that as negative 2 divided by negative 1. If we simplified that, we would just get back to positive 2. But thinking of it in this way now allows us to interpret the denominator as a negative change in x values. So instead of going 1 to the right, we are now going 1 to the left. And then instead of going up 2 for our change in y, we can now visualize or think of that as going down 2. So left 1, down 2 will put us right there at that point, negative 1, 3, or at least it looks like that's the point we're going through. And that also looks like that may be our point of intersection. So let's just go ahead and finish graphing that orange line, connect our dots. And then it appears that our point of intersection is looking like it has an x-coordinate of negative 1 and a y-coordinate of positive 3. I put a question mark there because, well, our graph looks like that is the point of intersection, and those points of intersections are the solutions to our system of linear equations, but we've seen before that our graphs drawn by hand don't usually have a great scale, so we may be kind of visualizing that wrong. So how do we know for sure if negative 1, 3 actually is a solution to our system? The way we can verify that is by seeing if it actually satisfies or is a point on both of our lines. So let's see it. On our first line, y is 3, x is negative 1. So is 3 equal to negative 1 plus 2? It sure is, right? I just plugged our x and y value into our equation up here and then just verified that it gave us a true statement. So negative 1, 3 really is on our green line, and that's good. How we found that point initially was by working with the orange line. So we know it's going to be on the orange line, but we can verify that in the exact same way. So if we plug y equals 3 into our orange line equation, along with x equals negative 1, we get 3 is equal to 2 times negative 1 plus 5. But the right-hand side is negative 2 plus 5. and negative 2 plus 5 is positive 3. So the point we saw actually was the point of intersection. Negative 1, 3 is the point of intersection between these two lines, and is also the solution to our system of linear equations. So solving linear systems graphically is how we always do it initially, because it gives us this great insight into the geometry behind the scenes. But we really do want to very quickly move to solving these systems algebraically, because our point of intersections or our solutions will not always be these really nice values that we can visually identify. If our point of intersection was some weird fraction like 1/6 or 4/3, then we're gonna have a lot harder time kind of just looking at our graph and picking the right X and Y coordinates. So we want to move away from doing this graphically and figure out how can we solve the system algebraically instead.